4. Test about a population mean. I'm not sure. If I could choose to eliminate flies, mosquitoes, or wasps, if I had to pick one of those, I'm not sure which one I would choose. I think the mosquitoes would be the front runner for me. Yeah. Okay, there's 2 tests here that we're going to talk about. Um, they are the first 2 in the calculator when you go to stat and then tests. There's the z-test and the t-test. And if you remember, the z-test, or the z, when we're talking about population means, is a time where you'd have sigma given to you, a population mean given to you. And the t-test would be when you have to calculate, or it's been calculated, the standard deviation for a sample, right? That's how you choose between which test. The conditions are what we've seen before. SRS, right? That's consistent for all tests that we've seen, or all tests or confidence intervals. The 10% rule, that's also been consistent, no changes there. But now that we're talking about means, we also have normal. But if it's a t-test, if we're using a t-distribution, does it really have to be normal? The answer to that's no, it doesn't. If n is greater than or equal to 30, well, then you have the CLT and you've got no concerns, right? We're happy. But I think you're going to find that that's not going to be the case in a lot of situations. So when n is less than 30, we need to show or see that there are no outliers or massive skew. And to be honest with you, I'm not sure what a massive skew would look like without an outlier. I'm just saying, that's just my thought on that. But it doesn't have to, if you look at it and it's got 2 peaks or it's kind of a weird shape, but you don't have a really large skew or an outlier, go forward. Yeah. So this does not have to, it doesn't require absolute normality. So it just can't be too scattered. If it's a z, then it has to be normal. So n is greater than 30, then you have the CLT, and you're good. Or the graph looks at least roughly normal. And when we say roughly normal, if you can believe that it's heading in a normal direction, go ahead with the calculations. We actually want to look for excuses to do the calculations more so than excuses not to. I think the conditions come across as rules that you absolutely have to follow, and that's true. But at the same time, we want to bend them as much as we can to make sure that we can make the calculations. And if you break a rule, if you feel that a rule is broken, that's fine. Do the calculation anyway, and at the end in your conclusion say, yeah, but this maybe isn't normal enough for this calculation to be correct, or something like that. Make note of it, but still do the calculation. Okay, so we've got a couple situations there. We got the hypothesis. Ho versus ha. We're getting used to this, I think. And let me get zoomed up there a little bit. Our calculations for t would be x bar minus mu, and I'm going to put a little o there, this is a naught. This is mu sub naught. That's just the claim. It's what the claim was made to be mu over Sx divided by square root of n. So it's the same calculation as we had in chapter 7. This really isn't any different. It's just whatever the claim is. It's the ho. Okay, it's the value of the ho. So this is the claim. And again, it's really a lot more likely that you're going to run across a t distribution than a z distribution. Because how often are you going to know a standard deviation when you don't know a mean? It's probably not going to happen. But it can. So in that case, it's z equals x bar minus mu sub naught, again, just the claim, over sigma divided by square root of n. And then both of these translate to a p-value that we compare to alpha. And what's alpha? A line in the sand. Yeah, that's how I think of it. A line in the sand. All right, bully. Here's the line in the sand. You step across that and you're dead meat. Oh, you stepped across that. Okay, I'm going to move it here. You step across this one and you're dead meat. All right. So, the shortcuts. A t-test and z-test. We still have our conclusion. We have significant evidence to reject the null, or we fail to reject the null, we don't have significant evidence to show whatever it is that we're trying to show. So we'll get those conclusions no, let's write those in. Never mind. Everybody good? You with me? Sydney still got some writing going there. Gosh, if you guys had known about the t-test and the z-test and the one prop z-test in chapter 7, it might have been a different world, right? Well, your teacher's a real jerk. You still need to know the formulas. They're still valid, because what if they give you everything but one piece of it and you have to work it algebraically backwards? So that's why I didn't share with you any shortcuts in chapter 7. All right. So, statement. Your statement should look something like this. If we're rejecting, we have significant evidence to reject the null and conclude and then we want to say something about the context of the alternate, that the alternate is true. And then the context is huge. here's why. I made this comment yesterday to a student, and I thought, wow, that's the first time I've really sort of put it in that framework. Because as a student, you can sort of be programmed to get through a problem, right? Here's the program, here's what you say. But if you can do that and put it into context, then you understand what the answer to the problem really is. So that's you know, we don't want you just programmed, we want you being better than that. The fail to reject, we would say we fail to reject the hoe and conclude there is not significantly, or there is not significant evidence, and then context of the ha. So the key thing is here, significant is reject, not significant is fail to reject. Mistake I see in the conclusion for the fail to reject, and I see it every year, is somebody will say we fail to reject, or we have, here's how they usually say it, we have significant evidence to fail to reject. Now, having significant evidence means that you're in a tail. Failing to reject means that you're not in the tail. So it's contradictory to say something like that. So your evidence is either significant, it's in the tail, or it's not significant, you're in the body of the curve. Okay? All right, let's look at a problem. 65. Let's see, this is on page 606. If you want to turn there with me. Attitudes. In this in this problem, it's the survey of study habits and attitudes. The SSHA is a psychological test with scores that range from 0 to 200. So SSHA test. 0 to 200 are my scores. The mean score for U.S. college students is 115. That's going to be our mu sub naught, our claim. The teacher suspects that older students have better attitudes towards school. She gives the SSHA to an SRS of 45 students from more than 1,000 students at her college who are at least 30 years old. So, so this is the null. The alternative, this teacher thinks that for older students, the mu is greater than 115. And she has an N of 45, it's an SRS, out of more than 1,000 so big N, big N is more than 1,000. Okay? And the teacher wants to perform the test. It gives the null and the alternative. And the first question in 65 is just, are the conditions met? Let's check and see. Is it an SRS? Yep, that was given. Is the 10% rule in place? Yeah, 10% of 1,000, more than 1,000, let's just say it's 1,000, is greater than 45. So our 10% rule met. And let's see, is it normal? Yep, because 45 is greater than 30, so it's normal by the CLT. So our conditions are met. And that's as far as 65 actually asks you to go. But the problem comes back up in 71. '71 asks us to do more with that. So let's see if we can't finish this problem off. In this, it says that the mean score for these older students was 125.7, so that's going to be X bar. And the sample standard deviation, SX, is 29.8. So now we have everything to put into our standardizing formula, or is this a t-test or a z-test? T, right. So when we're dealing with t, the one thing we probably want to write down is degrees of freedom. What would that be? 44, yeah, 1 minus the 45, 44. But we don't totally need to worry too much about that if we're using the calculator. It's going to take care of that for us. So let's go to a t-test. So stat, tests, t-test. In this case, we have stats, not data. So if you had a list of values, you could use the data and just tell it where that list is. So our mu sub naught in this case is, let's see, what do we have, 115? And X bar is 125.7. And SX is 29.8. Let's see, what do we have? We've got 45 for sample size. And she thinks that it is greater than. That her mu, the average of the older students, is greater than the average of all students. So a t-test gives us T is 2.41, P is 0.0101. Throw that out there just in case we're looking at something. Let's see, X bar, SX, and N we've already got, so I don't know that I need to write those. Okay. So now, I'm comparing this to what? Oh, alpha is 0.05. That was given earlier. I didn't write it down. Alpha is 0.05. Put that up here. So is alpha, or is the p-value of 0.0101 less than or equal to alpha? And for sure it is. So, and way less. So we reject the null. So we have significant evidence. To reject the null. And conclude the older students do score higher on the SSHA test. I do think that the questions in 71, you might look back at those. It asks to interpret the p-value. I didn't do that here. If I were interpreting the p-value, I would say something like, in a sample, a random sample of 45 of these older students, we can expect a result as high as the x-bar that we got about 1% of the time. So it's not a likely score to get if the null is true for those students as well. So something along those lines would be great. I will tell